Hi and welcome to video 6 of this Unit 4, Topic 4 for Math Methods in the Queensland curriculum. And we're going to talk about cumulative distribution functions, and we're tacking this onto the end of the probability distribution of functions in a continuous random variable topic. So there's a cumulative distribution functions where we're talking about a continuous variable. So first of all, just note that we're talking about cumulative, which is kind of just an adaptation to the word accumulate. So it's an accumulative function that builds as we go, rather than the functions we dealt with earlier that are built up and then come back down. So let's have a look. Imagine a discrete distribution. We've got that set up there. The first question I've asked is, if these are all the probabilities, well, what goes here? And the answer, of course, is that we add all these up and we see what remains to make the total 1. On the assumption, of course, that the only possible outcomes are 1 to 7. And what remains is 0.05. So you can test that, and just remember that that's an important feature of probability, that the sum must be 1. Graphically, it looks like this, and of course the last point is down here. And it's a bit of a rough graph, but the point is still valid, that this is what our distribution looks like. It's not a very nice distribution. We can't see any distinct trend. It sort of peaks in here, but otherwise there's not much of a trend in there. But what we can graph is a cumulative distribution where we accumulate our values. So over on the right hand side, the probability that x equals x was here, but I'm actually going to change that now to the probability x is less than x. So x is less than or equal to 1 is 0.1. X is less than or equal to 2 is 0.15. We're accumulating, so it's a sum of those two. X is less than or equal to 3, we add the extra 0.1 on, we get 0.25. Then we get 0.45 by adding on the 0.2. 0.75, and of course this should sum to 1. So we get 0.95. and then we get 1. So then we have our probability that x is, and I'll change this scale to be less than, I'll just knock that off as well, or equal to, and of course our scale goes from 0 up to 1. And so for 1, it goes up to 0.1, I'm just sort of guessing the location, but hopefully you can see the pattern here. 2, it goes up to 0.15, 3, it goes up to 0.25, 4 it goes up to 0.45, 5 it goes up to 0.75, then 0.95, and then 1. And it's discrete data. We did introduce it as a discrete distribution, so it doesn't make sense to connect the dots. But of course this topic is actually on continuous random variables, so we'll also get something that tends to look a bit like it starts at 0 and it should build up, and it should always max out at 1. So we've got some really well-known things already, like our y-axis going from 0 to 1 in a cumulative distribution. So that's the introduction to what cumulative distribution means, and there's things that we can do with that. So if I take this probability density function, I've stolen this from exercise 16a, question 7. And it's a quadratic, it has x-intercepts at 5 and 1. So this is what the distribution looks like. This is not an accumulative distribution, it's just a distribution at the moment. So you can see there in the area below the curve is 1, which is actually really nice. And so a cumulative distribution doesn't do a great deal, but it helps us a bit in some areas. So if we wanted to consider graphically the probability that 5 is less than or equal to x is less than or equal to t, it's going to look more like this. It's going to start with 5 being 0. The probability that 5 is less than 5 is 0. And then it's going to build up, and of course it peaks in the middle. So that's where we're going to get our peak on the original graph, which will be the steepest point, the steepest tangent on our cumulative graph. It's the highest rate of change because it's the turning point in the original. And then we're going to get our 1 up here. And so you can see here that we're actually looking at something that looks distinctly like a variant on a cubic function. And that makes sense because we're dealing with a calculus relationship here. Now the area is irrelevant in this type of function, so just keep that in mind. The area doesn't help us with anything because the area below this curve is something else. But we can find probabilities as an accumulative value. So the probability that x is below whatever this point is here, let's say it's 8, is just literally going to be the value on the y-axis. So if you can determine the value on the y-axis, you're good to go. And of course, if you wanted to find the probability that x is between 7 and 8, 7 being, say, here, well, you would just find the difference between the probability that x is less than 7 and x is less than 8. So this would be your value, that difference there. So we can do a lot with it still. And if you know the function, it's really easy to find those differences if you know that function. What is the function though? That's the problem. We know that f of t is the probability density function. F of t equals 1 over 36, t minus 5, 11 minus t. So we call capital F of t the cumulative function. Then we get this. And to determine a cumulative function, we could do some modelling, and we could find, like for example, we could find if 6 is here, we could find that probability by calculating basically the integral. And so we run through this process. I've pre-done this process. There's an expansion there, and then we integrate that expansion. We substitute in 6 and 5, and we get 2 over 27. So that means this is 2 over 27. That's all good. It turns out that the actual function, this function here, well, it just represents the integral at any point. At 6, I substitute in 6 for t into that integration. At 7, I substitute in 7 for t into the integration. At 8, so on and so forth. So if I want to know what is the value of this function at this point, t1, I just substitute in t1 into the function, as I've sort of done here because I've got t. And so to complete this calculation, the actual general version of the function will be 1 over 36, the integral between t and 5, also I don't have to do that again because we've already done it, 1 over 36 times, let's do the integration, negative t cubed over 3 plus 8t squared minus 55t, close brackets, between t and 5, and that's equal to 1 over 36 times by, and the t stays the same, so negative t cubed over 3 plus 8t squared minus 55t, and then we subtract from that what happens when we substitute 5 into this. 5 cubed over 3 plus 8 times 5 squared minus 55 times 5. And I'll do a quick simplification here. You'll see it speedily on your screen. Oh, I forgot to put a joke in there. So here's a post-edit joke. The rotation of the Earth really makes my day. And there's your function, and you simplify that as you like, but that's where I'm going to leave it. So essentially, that's the function that's given up here. As to whether I've sketched it perfectly accurate, well, that's a different question, but the point is still valid, that we get that growth based on what's happening there. Okay, so let's have a look quickly at an example, and I've just taken the example from a previous exercise, but I'm now applying it to this type of question. The probability density function is f of x equals this, and earlier in a previous video we determined the value of k, and then we determined the probability that x was between 2 and 5. Well, we've got the value of k. Now we're going to determine f of x, the cumulative distribution function, and explain why f of x doesn't equal 1. So f of x, first of all, will be equal to the integral, keep in mind that x is greater than 0, so it'll be the integral between some point t and, x is greater than 1 and 1, whatever that t is, and it will be the integral of that function, which in this case is 4e to the negative kx. I'm going to be a little bit lazy. K is not a nice number, so I'm going to leave it as k in this integration, then I'll substitute it out in a minute. So that gives me 4, and it's integral, so 4e to the negative kx. When you integrate e to the negative kx, you get e to the negative kx, but divided by negative k, and we do that between t and 1, and so of course this is equal to 4e to the negative tx over negative k, so 4e to the negative kt minus 4e to the negative k over negative k. And I want to leave it as just a number and a function of t. So I've got 4e to the negative kt over negative k minus 4e to the negative k over negative k when I substitute that 1 in. And I just want to do that simplification numerically. So on my calculator, I've earlier calculated 4 over negative 1.202, which is k. And so that gives me the value of the coefficient here. And sorry, I've forgotten it already, which is negative 3.3278. Negative 3.3278 e to the negative kt minus, and I've done that evaluation as well, and that's negative 1 essentially, so just minus 1. And I suspect there's a slight rounding error in there because I've rounded my k, so it probably is 1 in the evaluation because we got k by doing a log base here or something anyway. And so that's my original function. Now, if we go back and sketch this function, the function 4e, so I'll just sketch that quickly here, and this is a probability density function. It's going to look like this because it's an exponential with a negative power because k is negative 1.202. And here's our value 1. Now remember, the area below this original function has to equal 1. But that area below is graphed in our cumulative function. So our cumulative function is going to look more like this. Remember, it goes up to 1. It starts at 0 at 1 because that's where we've got nothing. But then the highest point is here, so that's the largest rate of change. So it goes like this. And so the second part of the question was, why will f of x never equal 1? And the reason is that this actually carries on forever, all the way up to infinity. And there's always a gap here. It gets really, really small, but there's always a gap here, which means we actually have a carryover asymptote. There's our asymptote there. Here's our carryover asymptote. And that carryover asymptote will represent, as we get closer and closer to 1, infinitely close to 1, but will never actually equal 1 technically. So that's the reason why f of x will never equal 1. Okay, so you are right to do exercise 16e now on cumulative distribution functions, and all the questions are a bit like this, and it'd be good for you to build up your understanding of questions like this and what a cumulative distribution function does and how you can use it. All the best.